Can we check if you can hear me? Yeah, hi. Okay, so for the problem solving session, we're going to discuss, like Konstantina mentioned, the 2025 exam. And we'll begin with question 12, GPUs and SIMD. So the question reads as follows. So we define the SIMD utilization of a program that runs on a GPU as a fraction of SIMD lanes that are kept busy with active threads during the run of a program. And we saw in the lecture and practice exercises that the SIMD utilization of a program is computed across the complete run of the program. And they've provided with for us a code segment that would run on the GPU. And this particular GPU has 32 streaming multiprocessors. Basically, all of these units can compute together in parallel, right? There's 32 of these. And a warp consists of 32 threads. And each warp runs on a streaming multiprocessor. So essentially, you have 32 warps, right? And each thread will execute a single iteration of the shown loops. We have 1024 iterations, which means one iteration per thread. And you have 32 threads per streaming multiprocessor, and you have 32 streaming multiprocessors. Does that make sense? Good. And the question is that let's say we have two arrays B and C. The data values of these arrays are already in the vector registers. So we don't have any loads and stores to these arrays. And then both B and C are arrays of non-negative integers that range from 0 to 10. And these values are sampled from an arbitrary distribution. Okay. The questions are, how many warps would it take to execute this particular program? And how you would do this is the following. You would first, like we saw here, that we have 1024 number of iterations. So number of iterations is 1024, which basically means these are the number of threads you need, right? Because every thread maps onto one iteration. And you've got a total of 32 threads per warp. And this should give you the total number of warps you need, right? Total number of warps would be the total number of iterations or threads that you need in total, divided by 32, because there is 32 threads per warp. And that gives you 32. That's the answer for the first question. Is that good? Okay, I assume that that is good because there were no questions until this point. And here's where it gets more interesting, right? So if the condition for the if statement is b of I not equal to 0, so let's go back to the question and see that there's a conditional statement here at the top. So we have if condition, and then based on that condition, you execute instructions 2 to k. So there's a grand total of k instructions. The first instruction is the condition itself. And everything else after this is what's in the conditional statement, within the conditional statement. It's executed only when the condition is true. And the question reads, if the condition for the if statement is b of I not equal to 0, and there are 12.5% of b's elements that are 0, which means that the rest, which is 87.5%, are non-zero. So there's 87.5% of those elements that would go into this condition. It will be true under this condition. So the question at the end of the day is, what is the SIMD utilization achieved by that program? And you should assume that there are no further control flow instructions in the body of the loop. So instructions 2 to k have no other control flow instructions. They're all let's say, right, non-control flow instructions. And this is the question. Basically, you have to compute the SIMD utilization. And again, to go back to what SIMD utilization is, it is computed across the program, and It is the fraction of SIMD lanes that are kept busy with active threads, right? Now, for the purposes of this solution, what you would then start with is there are 1024 threads because there are 1024 iterations. And out of these 1024 threads, you will have 87.5% of these that actually execute something, correct? The rest won't execute anything. And these 87.5% will execute K instructions. The rest, 12.5%, will execute just the one instruction. Does everybody follow until here? I think everybody follows until here. So how you would compute the result is 12.5% of the total number of threads, which is 1024, would execute one instruction. The rest, 87.5% of the threads, would execute K instructions. And the SIMD utilization would be that you divide this by assuming a case where all 1024 threads run K instructions. So that is what this will be. This will be the solution. This gives you the SIMD utilization. And clearly it's not 100 because there are 12.5% of the threads that do not run K instructions. They are stalled. Is that good? Does that make sense to everybody? You have a question, go ahead. Yes, you can. Yes, you can. You don't have to simplify it at the end of the day. Of course, it helps, but we also understand that you have many other questions to answer. So you can leave it here as long as you show the steps that you use to compute the result and that it shows that you understand the question. That's sufficient, basically. That's the learning part of the course. Yes?
Just say one more time what the CPU utilization is. So it's a fraction of the active or busy lanes over the amount of all lanes.
Exactly. So let's say you have K instructions that the K slots, K instructions that you run. You're trying to compute how many of these K instruction slots are you occupying? How many of these are you utilizing? And that's what the SIMD utilization gives you. And how many slots do you have? It's 1024 into K because there's 1024 threads and K instruction slots. And how many you utilize depends on whether every thread is executing an instruction every instruction slot. In the concrete example that we have here, the 12.5% threads that do not enter the condition or do not have a true conditioner, they execute just one instruction. And that's where the SIMD utilization drops. Good. Then we will go on to the next one, which is even more fun. So here's the question. So let's assume that the if condition that we saw, so let me bring back the if condition for you. That's the if condition. And if it's true, you get into the if condition, right? So if the if condition was that B of I is not equal to 0, and along with it, C of I was not equal to 0, basically the case where both B of I and C of I are 0 is when it would not enter, right? There will be, and the additional information is that there are 12.5% of B's elements that are 0, like the previous question. And in addition, 25% of C's elements are 0. All right. The question is, what is the maximum SIMD utilization and what is the maximum possible SIMD utilization and minimum possible SIMD utilization? And again, you assume that there is no control flow and the probabilities are independent. They're sampled from independent distributions. And you're supposed to show your work of some example data layouts of B and C that would result in maximum utilization and minimum utilization. So let's think about the condition a bit more and why there might be a spread of utilizations. Think of a scenario where you have the 1024 threads of B, the 1024 elements of B and C. And it so happens that all of B's zeros coincide with all of C's zeros. This is one possible case. Another possible case is all of B's zeros do not coincide with all of C's zeros. And these gives you two contrasting cases that map to maximum and minimum SIMD utilization based on the condition that we have. So the condition when it enters the thread, enters the if condition, and provides you utilization is that B of I is non-zero and C of I is non-zero. Naturally, the maximum utilization should be the case where all of B's zeros are completely match all of C's zeros at the same indices. And if they're not, that would give you the minimum utilization. Does this make sense? Does this line of thinking make sense to everybody? Good. Then let's take some examples. To begin with, for minimum utilization, what you would have is something like you have B and you have a bunch of zeros. And these would be a total of 128 because you have 1024 elements. 12.5% of these 1024 is 128. So you will have a stream of zeros for 128 items, and then you will have some non-zero value, right? So let's assume it's 1 for the sake of ease. You have a bunch of ones, and that is going to be the rest, 1024 minus 128, whatever that might be. In the case of C, in this particular context that you want minimum utilization, the zeros would again map perfectly to these cases so that you get the if you want minimum utilization, these wouldn't map at all. They would be completely different. So you would have ones for 128 items and then zeros for 256 items because there are 25% zeros in C and the rest would again be 1. Does this make sense? Do you follow me until here? Are you sure? You can ask me questions if you're not. You seem confused. Okay, it's good. It's good.
Yeah, so we want the minimum, so that basically every time that the K instructions are loaded, it don't load.
What it means is for the minimum utilization, you want as few threads as possible to run K instructions, which means you want as few threads as possible to enter this condition, the condition that B of I is non-zero, C of I is non-zero, both together. So in this case, you see that there are 128 plus 256 elements. And you can't go more than this, right? Because there's only 128 and 256 elements that are 0. Does that make sense?
Yeah,
so the same, if we were to do for max utilization, what would happen is, let's say, again, you have all the zeros to begin with, right? The 128 items. And the rest are, again, all ones. What would it be for C? It would be all the zeros in the beginning for 256 elements and all the ones, right? This will give you the maximum possible utilization. And now if you were to compute it based on this example, based on these two polar opposites, for the sake of min SIMD utilization, you would have something like the following. You would have a total of 128 plus 256 elements. Or let's say threads that would execute just one instruction. And the rest, which is 1024 minus 128 plus 256, would execute K instructions. And to get the SIMD utilization percentage, you would divide this by 1024 times K. Does that make sense? And if you were to do the same for max SIMD utilization, you would basically have the first 128 elements that would not give you K instructions. It would be just one, right? So you have 128 times 1 plus 1024 minus 128, and these would execute K instructions. And to get the total utilization, you would divide this by 1024 times K. Any questions up until this point? Or did this make sense? Okay, perfect. Then we move on to the next question. Oh, do you want to take a look at the answers still? Okay. Good. Then we have memory potpourri. This should be a point where you can score all the points. Basically, the idea is that you answer true and false based on whether you see that things are correct or not, right? So the first one, a large fraction. Oh, also, we will subtract 2 points for each incorrect answer, and you would be awarded 0 points for each unanswered question. So there is negative marking here, right? So a large fraction of modern systems, example, the Apple M1 chip and the IBM Power 10, is composed of memory structures. That is, they contain caches and a main memory hierarchy. This is true. Then an SRAM cell loses charge over time and thus requires periodic refresh operations. What's an SRAM cell? It's a static random access memory. Does it lose charge over time and does it need periodic refresh? It doesn't. What needs periodic refresh? DRAM needs periodic refresh, that's right. In a typical 6-transistor SRAM cell, 4 transistors are used for access and 2 are used for storage. Is that correct? That is not correct because it's the other way around. The access transistors are 2 and the rest are for storage. Okay. Compared to DRAM, 6-transistor SRAM cells have lower density than 1-transistor, 1-capacitor DRAM cells. This is true because you objectively we have lesser transistors, lesser space occupied. Then you have DRAM manufacturing process is exactly the same as CMOS logic manufacturing process. So think of, let's say you have a fixed amount of space and you're using 6 transistors for 1 bit, which is what you would do in an SRAM. And on the other hand, you have 1 transistor and 1 capacitor. You can pack many more 1 transistor plus 1 capacitor in the same area compared to 6 transistors for 1 bit. Which means that you can pack DRAM more densely than SRAM. That's what I meant. And how does it tie to this question? Is because 6-transistor SRAM cells to store 1 bit of information need more space than a 1-transistor, 1-capacitor DRAM cell to store 1 bit. Therefore, it is it has a lower density than SRAM has a lower density than DRAM. No problem. So DRAM manufacturing process is exactly the same as CMOS logic manufacturing process. This is untrue. You need tailored manufacturing processes for these. DRAM is not susceptible to read disturbance errors, example, RowHammer. This is false, as we've seen in the lectures and many talks. Compared to DRAM, phase change memory has a higher access energy. This is objectively true. There's not much to say here. TCM loses its data at the loss of power. Is this true or false? Correct. While DRAM and flash are charge memory technologies, STM RAM and memristors are resistive memory technologies. Is that true or false? That's true. These are basically resistive based, and these are charge based, DRAM and flash. You maintain charge and try to refresh charge basically. Flash memory has a higher cost per megabyte than a hard disk. Is that true? That's correct. It is true. Main memory is larger and slower than caches. Is that true? It should be true, right? L2 cache has a lower latency than L1 cache. Is that true or false? L2 is objectively farther, right? So is it true? It is false. L2 is farther away, right? And it's bigger in size. The L1 cache is closer to the processor, so you need lower access latency. Yes, exactly. So this is false. Increasing the associativity of a cache increases the cache hit rate while also increasing the cache access time. Is that true or false? Sounds true. Is it true? It is true. It is true. Most modern processors do not implement true LRU, also called perfect LRU, in highly associative caches. Is this true? It is true because it's expensive in terms of area to maintain perfect LRU because you need to track across all the ways. Sorry, least recently used. So you try to maintain which line was least recently used so that you evict it first when you bring in something else. And it's expensive to maintain true LRU, which is the least recently used. So you use an approximate way of doing things. Cool. Number of ways in a set associative cache is always one. Is this true? It's not true, it's false. There's a completely different cache that has only one way all the time. I will leave it to you to check. Okay, that's me then. That's memory potpourri. Any other questions on memory potpourri? No. Perfect. Then I think Umut is going to take over next. Test, yeah.
Hello. Now we will look at some Boolean circuit minimization questions. In this question, we are given some minterms in the sum of products forms, and we are asked to simplify this Boolean equation. Since minterms have 4 bits, we can use 4 variables, and we can start with naming them by A, and we can go B, C, and D as we go forward. So we can write this function as A, B, C, D, or A, B, C, D bar, or A, B bar, C bar, D bar, A, B bar, C bar, D, A, B bar, C, D, A, B bar, C, D bar, and A bar, B bar, C bar, and D bar. Now we can check which pairs have only one disagreeing variable so that we can just remove that and simplify the equation. If we look at these two expressions, we can see that they only differ by the variable D. So we can write this as ABC, D or D bar. And if we look at this one, we can write this as A, B bar, C bar, and D or D bar. And again, for this, and lastly, we have this one, but we haven't matched it with any other one. But since in the Boolean algebra, we can use the idempotent law. If you look at this one and this one, you can see that they only differ by the A variable. So we will just add this one again here so that we can group these two things as well. So F becomes ABC or D bar. And as you can see, we have order of complements here. So since something or its complements or is always one, so we can simplify this as ABC or A B bar C bar, A B bar C, and B bar C bar D bar. And we can still keep looking for the term pairs that only differ by one variable. As you can see, these two only differ by C, so we can merge them, group them together. So again, we have one here, and we have A B bar or A B C or B bar C bar D bar. But we are not done yet, because if you look at these two terms, they share one variable, and one of them has the negated version of the other one. So if we group them, we can see that this, we can see that this expression is either B bar is correct or C correct, because if B bar is correct, we don't care about C, and if B is correct, we only look at C. So we can simplify this as A B bar or C, and we have the B bar C bar D bar. And this is the minimized form. You can use kernel maps to verify, but I don't know about it.
Okay, so say I solve it with kernel maps to the halfway stage, would then that be like treated less generous because like if you make a mistake, yeah, you need points either way. You're not gonna lose 4 points. Okay. Fair enough. Okay, then that's the question. Thanks.
Yes. I couldn't understand the line. Could you please tell it again? Yes. It would be wrong because BC and B bar C does not differ by only one variable. It will be varying by two variables. So in that case, you would need B bar C or BC bar as well to just remove the term, to leave AB by itself, if this is the question. Okay. So I'm moving to the next question. And in this question, we are given a Boolean equation, and we are asked to convert this equation to only contain NAND operations. So at the end, we only want to have the expressions in the form of this. So before starting, let's recall two important laws. The first one is involution law. So that if we take the complement twice, we get the same thing. So it's equal without any complements as well. And the other one is the De Morgan's laws. So that if we take the complement of x plus y, we get x bar y bar. And if we get complement of xy, we get x bar plus y bar. So let's start with the function. We have a and b bar plus c plus a and c. So first, we can focus on this outer OR operation. We can use involution, put the negation inside, and we can apply the Morgan law to convert this OR operation. So we will apply negating operation twice, and we will just use this one. So if you think about it, we have the same expression here. We can say x to this part and y to this part. So we will get x bar, y bar. And let's not forget the outer one. And now we can apply this negotiation here to remove this OR operation as well. So we will apply the De Morgan's law again. So we will have and now we have double negotiation on AB. So we can use the involution law and remove this. So our function becomes AB C bar and a C bar, and let's not forget the outer negotiation. And now if we look at this parenthesis, we can see that we already have XY bar, and we can apply De Morgan's law here to convert it to a useful form here. So we will apply the formula. Let's not forget this one. So if we use parentheses like this, we can just simplify this term as C bar, because the inner term will always be bound to C bar, and even if A bar is correct, we need C to be 0 to make this be 1. So it becomes AB C bar, and let's not forget the outer one. Now, we don't want to have this C bar by itself because it will make things harder for us to move to other steps. So what we can do is we can add a 0 term to the equation. It will not change the equation, but it will help us to group the terms together. So we can make this, let me move this to this part. So we can add a 0 term here, and we will use A bar. Since we have the A and its complement in the same AND function, it's 0, so it doesn't change the functions itself. Then we can group with AB. Now, if we return back to this part, you can see that C bar or A bar is already an AND operation. We will just substitute this with C and A bar, and we have AB and CA bar. And let's not forget this one. And here we have a term, and it's already in the AND state. We need to convert it to the NAND state. So here we can again use the idempotent law. So instead of we can make it AB plus AB. We can substitute AB with any number of ABs because it will not change the result. So we are just repeating the same equation again and again. So if we substitute this with this, we reach this part. And here again, we can use involution law and De Morgan's law again to convert this to an AND gate. And let's distribute it to the inside. It's in the summation form, so it will become A B bar, A B bar, and we have this bar. We have C and A bar here, and we have the outermost bar. So this makes, here we have an AND gate, here a NAND gate, and their inputs, their outputs goes to this NAND gate, and here we have another NAND gate, and again, their outputs goes as another NAND gate. So our function becomes like this. Do you have any questions?
So, strategy to get result, I think just modifications, so more likely than not, in one direction, right? So, what is your strategy?
Like, actually, my strategy is trying to make the equation in the form of that we can play easily. But actually, there are some parts you could go in different ways, but get a correct result as well. For example, since we reach this part, actually, you don't need to add a 0 value to, like, in this part, you don't have to do this. Like, you can go from C bar and you can get a NOT operation, again using NAND gates. So you can go from that part as well.
So what I have seen before, some people do it, but then again, it's quite cumbersome. But since NAND and also more logically complete, you could just express AND gate basically in terms of NAND
Yes.
and so on. Then we could just do this for every expression we see, but it's a bit cumbersome. So
Well, like in that case, for each of the operand, yes, you can express it with NAND gate, but I think with directly converting each of the expressions, it would be much error prone, I would say.
So like just simplify the expression as much as possible.
Like as in algebra, sometimes you need to add and subtract the same amount to make the equation much easier to solve.
So it requires some creativity, is what you're saying.
Yes, maybe there are some special tricks, but what I do is like try to make it into some form that I can apply basic laws to get in a form that I want to achieve. Then I will continue with the next questions. Now we have some questions on Verilog, and let's look at the first one. The first one asks the difference between a blocking and non-blocking assignment. As you might know, for blocking assignments, we use normal equals sign. And let's have an example with both blocking and non-blocking part. And let's assume that we have an input that let's assume that at t equals t1 time, our input I gets 4. And let's say that we are doing blocking assignments. And let's say that A gets its value from I and B gets its value from A. In that case, blocking assignments are literally blocking, so their execution follows the order. So first, A gets the value of I, in this case 4, and after that, this expression is handled. So B also gets the A's recent value, which is I. So in that case, A equals I and B equals I. So, but in the other case, if you look at the non-blocking assignments, and let's say that for some t equals, for some t less than t1, let's say that A had value of 3, and we have A gets I's value and B gets A's value. In this case, after these values are applied, we see that A gets the I's last value, but B gets A's previous value, because these operations does not wait for previous ones to complete, so they are executed currently, in a sense that. So the difference is, in the blocking assignments, there is operations are handled in series, but in the non-blocking one, they happen concurrently. So changing the value in the same block does not affect the next instruction's value if they got assigned to a new value at the same time. Is there any questions? Yes. Actually, for blocking ones, you usually use it for combinatorial things, and non-blocking to sequential things, so that you actually let some data in some state, and you get the value after the next clock cycle, right? But in the combinational, in a blocking way, let's think about it like, yes, they have the execution, or they follow execution order, yes. I think the reference answer was just like this. No, I will just explain verbally. I was planning to explain verbally, but I don't know this way.
Seems like an explanation by example. And I'm asking,
Yes.
is this acceptable for the example?
I think Konstantina could answer this better.
So the way this explained is by an example, right? And the solution has like a sentence where it says this means this and that means that. It just gives a concrete example. So when you are asked to explain something, can you just provide an example like he did, or is that?
In this specific case, you should also write like a sentence.
Okay. Then let's continue with the next question. In this question, we have given a Verilog module, and we have some questions. And let's first look at the first part of this question. It asks, what does this module do? And let's look at its code. And we see that when reset is triggered, we are setting some registers to 0. And if reset is not on, we see that if X reaches some value, it gets resetted. And if it didn't hit this value, it's get incremented. And if you look at one more level, if X has been reached its target, and if and only if X has been reached to its target, so X counts from 0 to 60. And if X has 59, so it's in the 60th iteration, we see that Y gets incremented by 1. And also, if Y reaches its target 60th iteration, we see that Z gets incremented by 1. And this register goes to up to 23. So it's counting 24 values. Y goes to 59. So it counts 60. And X goes to 59 again. And this, in each level, we see that after this completed, the other one gets incremented. And it continues until the last register. So as you can see, we first increase X up to its 60th iteration, then we increase Y by 1, and again we increase Y up to 60th iteration, then we increase Z by 1, and we are counting towards until the 24th iteration. So it basically counts the time in the sense of seconds, minutes, and hour. We can just explain it as it increases its counters as if they are seconds, minutes, and hours. Are there any questions on this? Now let's look at the next question. And in this question, we are told that after we reset the module and waited for 3 hours, when we probe the signals, we see that the hour 1 got 1, and minute 1 got the 15 value. And we are asked, what's the frequency of clock signal? So if we turn back to this question, as you can see, for each positive edge of the clock, we are increasing the counters by 1. So in each cycle, we are incrementing by the levels, according to the levels, as if they were seconds. So what we basically can do is we know the frequency is clock cycles that we performed by the time, like how many clock cycles we are doing in 1 second. So if we get the ratio of clock cycles and time, we will get the frequency. So how many clock cycles did we pass? So since this counter counts hours, we will have to multiply this by how many minutes it passed and how many seconds it's passed. And since this counter counts the minutes, we will just go to seconds as well. And we don't have the second part. And we know that the real time that this module spent is 3 hours. 3 hours is this many seconds. So we can group them like this. Which is 5/12, which is equivalent approximately 0.416 hertz. Any questions? Now, in this question, we start with an explanation. It says that the duty cycle of a clock signal determines the percentage of time the clock signal spends in the logic 1 state. After the example, I will try to show it with a basic plot. For example, a 75% duty cycle, 0.25 hertz clock signal is in the logic 1 state for 3 seconds before transitioning to logic 0 state every clock cycle. So it basically says that for a clock signal that has a period of 4 seconds, it keeps the clock in the logic 1 state for 3 seconds. So if we look like this, and assuming the clock had a positive edge on time 0, we stay in the logic 1 state for 3 seconds. And since our frequency is 0.25, so our period is 4 seconds, our rising edge is here. So it's an example to what duty cycle means. And it says that you are given 150 megahertz, 50% duty cycle clock signal, and you are to design a frequency divider module that outputs a 1 hertz, 25% duty cycle clock signal and takes 150 megahertz clock signal as input. And design the module using Verilog, explain your design decisions. So as you can see from the hint, we are, again, we can still use a counter for these purposes. Like if you look at this example, as this X, Y, and Z counters counting time, we can just make the clock output when our counters hit some target. So since our original clock rate is 150 megahertz, and we want a 1 hertz clock, we have to spend 150 times 10 to the 6 clock cycles to make 1 period of clock cycle. So we have an input clock frequency of 150 times 10 to the 6, and our target clock has 1 hertz. So we need to make this clock slower by this much amount. So if we count until this point, we will be spending that many cycles and we will be outputting one value so that we divide our frequency by that many amount. So we need a counter to count to that number. So since it's between 128 times 1024, since it's between 128 megahertz and 256, we can just say that it's 8. We need at least 28 bits to store that many. We need that many bits to at least hit to this counter value. So we will have a counter of 28 bits. And again, with a previous example, you can assume that, sorry, let me try to make this better. Let's assume that our module is named frequency divider. And we have an input clock. And we will output the slowed down clock. And we will need to count to that number to make sure that we have a frequency of 1 hertz. Actually, we are going to follow the same approach. In the reset, we are going to reset it, and we will increase our counter by in each clock cycle. So if I write this very quickly, now to just follow the same example here, we will start with positive edge of the clock in the reset. And we are going to count until this number. So we are just going to follow the same approach here until we hit this number. We are going to count. And when we hit this number, this means that we have completed one cycle. And since we started with a positive edge, we will make it again a positive edge. And we will restart the counter. But the problem is we are asked to have a clock signal that has 25% duty cycle. So, which means that only 0.25% of the time the clock signal will keep high and it will follow this trend. To make this, we have to also keep track of how much time we spend while keeping the clock is on. So how we can do this? We can just get the 1/4 of this number, which we have the period of, so that when we hit this number, we can make the clock signal 0. Then since we already spent that much part of the period, so we spent 0.25 seconds, we will make the clock signal go to 0 so that our duty cycle will be only 25%. And this will continue with while closing the conditionals. So basically, there are many ways that you can solve this question. Basically, you need to follow how much of the time that your clock out signal, the reduced clock, should keep the one state, and how much you need to divide your clock frequency for the output clock. And if you look at the last question, it's directly about the previous question. It asks us, when we use the output of your frequency divider module as input for the mysterious module, how long does it take in whole clock time for Z to become 2? In that case, if we check this part, you can see that we are only interested in the positive edge of the clock. And since our period is 1 nanosecond, it doesn't matter whether our duty cycle is 50%, 75%, because since our period is 1 nanosecond, the positive edge will come at this point, so that duty cycle is not important. So for since we are generating a clock signal with period of 1 second, it will take equal amount of time to reach the clock to get the 2 hours. So it's again 2 hours. So basically, duty cycle doesn't affect the time that the counters in the timer increase, because the period is fixed. We will just consider the period for increases. I have probably many syntax errors. Yes, there should be an always at. Yes. No, register should be outside of the always at block. No, I think he asked whether we have to define the register inside the always block or not, but we define it outside the always block. In that case, since we are using non-blocking assignments, my original code has rec, but in that case, you could also have it basically a state. You could combinationally derive such signal as well. Oh, yes. Basically, like we are asked to have a clock signal that keeps its logic 1 state only for the 1/4 of the time, right? The question, did I understand your question correctly? You're asking about this part, right? Why we have such a control, such a check. In this question, we are asked to have a clock signal, and it has to have a duty cycle of 25%. So within the one period of the clock, only 25% of the time, the signal should stay at the logic 1 state. So since we are having a clock that is 150 times 10 to the 6 times faster, we are counting that much amount so that we can have a clock signal that has period of 1 second, right? Because in each second, we are increasing by this amount. Because, sorry. In each second, we increase our counters by this amount, right? So if we reach this value with 150 megahertz clock, that means that we spent 1 second. So we are counting up to that number, and we say that we completed 1 period of clock time. So we have a pos edge, and we got the new pos edge at this point. We have a 1 period. And we are asked to have 25% of duty cycle so that we want to keep our clock signal at logic 1 value only the 25% of the period time. So we need to make it go to logic 0 and keep it logic 0 until we complete the period, right? So we need to calculate how many cycles that we have to keep it as logic 1 state. Since we are only getting to 25%, if we divide this, we get this value so that we get 0.25 seconds. We count up to 0.25 seconds so that we can now make the clock signal go logic 0. Welcome. I think the next person can come.
Can you hear me? Good. So the next question is FSM. I'm going to read the question. Draw a really finite state machine, one whose output depends on both the current state and the inputs for a digital circuit that has three 1-bit inputs, A, B, and C, and one 1-bit output, D. The circuit checks the values of A, B, and C in the current and the past 2 clock cycles and sets the output value D to 1 when the following formula is true for all t, t-1, and t-2. This formula. Okay. Once the output bit is set, it remains set for the next clock cycle, t+1, regardless of the input values. And the state machine that you guys have to produce should use as few states as possible. We're going to assume that at the initial state, for the last 2 clock cycles, A equals 0, B equals 0, and C equals 1. And again, the usual instructions. Please clearly and comprehensively define each state. So what you need to think here is that you need to take into account 4 different time steps. T, t-1, t-2, and also t+1. So that means that you're going to need at least 4 states to write this. Actually, you need exactly 4 states in this case. So let's start with 4 different states. Let's call this S0, S1, S2, and S3. And now you should evaluate basically when this holds true, when this formula. And without going into all the nitty-gritty details and doing the like calculations, you transition from state S0, which is t-2, like the beginning of the state, to S1 when you have A, B, and C equal to 0, 0, 0, because in that case, this is going to be 1 and this is going to be 0. So the output of all this is 1. And then 0, 1, 1, 1, 0, 1, and 1, 1, 0. And with an output of 0. Because remember, to have an output of 1, you have to have this formula hold for 3 consecutive clock cycles. If that doesn't hold, then you go back to the previous to this state. No, let's take it in a different way. For all the other cases, you remain in the same state because this makes no forward progress. So that would be 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Again, with an output of 0. Yeah. Sure. Yeah.
Are we allowed to use this convention?
So I would write it down if you use this convention for simplicity, because it clearly states that you have to comprehensively define its state and state transition. Maybe like we would grade it like that, but I wouldn't leave it up to the grader to decide if I were you. You should write it down, like, and it's like in the general like guidelines for the exam that you should write any assumptions down that you make.
Because it can save a lot of space.
It can save you a lot of points as well. Yeah. Any other questions? Okay. So again, from S1, you are going to progress to S2 when these are the input values. And let's just call this all of this, for example, S. So for the values of S, again with an output of 0. But if you have all the other outputs, then you're going to go back to S0 and start from square one again, essentially. Let's call these T, again with an output of 0. Now from S2, you're going to progress to S3, again when S is the input set. But this time, you're going to have an output of 1 because it has held for 3 consecutive clock cycles, like for T-2, T-1, and this was T. So you're going to get 1 in your output. If it doesn't hold, in this case, again, you go and you start from scratch here. So that means that if you have T, you go back to S0 with an output of 0. And finally, when you are in S3, you know that you have to keep the output bit 1 for 1 more clock cycle because it was clearly defined here. It remains set for the next clock cycle. So here, even if you have T, which means that you have to go back to S0 since that doesn't hold anymore, you're going to have an output of 1. And if you have S, which means that this holds, you're going to remain in the state and have an output of 1. Does this make sense to you? Okay, in that case, let's move forward. So how many D flip-flops are required to implement the above FSM? Using one hot encoding, where each state is represented by a single bit, which is set to 1, and other states are set to 0, and binary encoding, where each state is represented as a different binary number. And in the case of the 1-bit encoding, you need as many bits as states. So that would be 1, 2, 3, 4. 4 flip-flops in that case. So 1 hot, 4 flip-flops, 1 for each state. Yeah, sorry for that. And for binary encoding, clearly legible, you need 2 bits to represent 4 different states. So that would be 2 flip-flops. As 4 states can be represented with 2 bits. Okay, good. Okay. Optimizing an FSM. So you get this FSM that has 2 inputs, A, B, and C, A, B, and 1 output C. And you need to simplify the state diagram and reduce the number of states. And what you're going to start with in this case is you're going to create all the state transitions between all the different states. Let me get this and use it as a ruler. I should be fine. Thanks. So here we're going to have state. We're going to have, say, input B, next state, and output. So let's start here, S0, S1, S2, S3, and here 0, 0, 1, 1, 0, 1, 1. Okay, usual. And now I'm not sure if you can see this clearly here, the state diagram, but anyway, I'm going to write down the next state from each initial state and with each set of inputs A and B. So this is gonna go like S0, S1, S2, S3, and then S0, S1, S2, S3, S0, S1, S2, S3. S3. And the outputs are gonna be 0, 0, 0, 0, 1, 0, 1, 0. Yeah, sorry. 1, 0. And what you need to observe here is that first, state 0 and state 2 here, you have always the progression to the next state, to the same next state, which is S0, S1, S2, S3, and again, S0, S1, S2, S3 with the same set of inputs. And also the outputs, they remain constant all the time. They're always 0. So essentially, you can merge these two states, S0 and S2. And this also applies to S1 and S3 because you again transition to the same states, S0, S1, S2, S3, S0, S1, S2, S3, with the same inputs. And the outputs are also same because they are 1, 0, 1, 0, and again 1, 0, 1, 0. So these are exactly the same states. Again, you can merge this. So let's call the merged S0 and S2 state a new state A, and the merged S1 and S3 state a new state capital B, capital A and capital B. And now I'm going to write this again. Let's use this. So now you essentially can drop entirely two states. Input A, B, next state, and output. So this is state A, remember the new state that we defined. This is B, 1, 1, 0, 1, 1. All the input sets. And then in this case, the next state is gonna be A, B, A, B. And this is done how? Like we replace wherever S2 or S0, we replace it with A, and wherever S1 or S3, we replace it with B. A, B, A, B. Again, like from here, you replace these and you come up with this. And the outputs are gonna be 0, 0, 0, 0, and 1, 0, 1, 0. And what you have to observe here is that there is one more trick you can do, which is that input A does not really affect anything at all in this case. And you have to notice that, which means that you transition from state A to state B when B is 1. The input of A doesn't matter. It always goes like that. So with 1, you go to B regardless of the value of A. And also with 0, you go to A regardless of the value of input A. And the same thing applies in the other state as well. So with 0, you go to A. And with 1 in input B, you go to the next state B. And it also doesn't affect the output at all. Because in state A, the output is always 0, so it doesn't affect it regardless. But in B, you get 1 when input B is 0, and 0 when input B is 1. So it means that you can disregard this entirely, and you can come up with this new state diagram that also eliminates input A from the calculations altogether. So A, B, you remain in state A for anything in input A, and with 0 here, again with an output of 0, you go from A to B with anything in A and 1 in 0, in input B with an output of 0. You remain in state B with anything in A and when B is 1 with an output of 0, and you go from B to A like this. And like this is as simple as this FSM can get. Yeah.
Could you state under what conditions you are allowed to, well, from a diagram like this, conclude and merge two states?
Yeah. So here you have to see that. Let's hide this and this. The next state of S0 and S2 is always the same with the same set of inputs. And this also applies to the outputs. So essentially, you have two identical things. The transitions are always going to be the same. You have to have the condition is that under the same inputs and outputs, the next state and the output is going to be exactly the same. And this holds for S0 and S2, and it also holds for S1 and S3. Does this answer the question?
Yes, more or less.
Yeah.
So basically, we have two sections of the traditional tape that are identical.
They're identical, exactly identical. So then you can merge it.
Yeah, completely identical.
They have to be completely otherwise it's not the same. Okay. I think this completes this question. And next up, I'm going to go with some pipelining questions. Okay. So consider a machine implementing the MIPS ISA. The design of this machine is very similar to the MIPS processor that was discussed in the lectures, with five pipeline stages and one ALU. And you have these stages that are fetch, decode, execute, memory, and write back. Each takes one clock cycle. The processor implements data forwarding and branch prediction. And when there is a flow dependence, it forwards an operand from the memory stage or the write back stage to the execute stage. And the load instruction can only be forwarded from the write back stage because data becomes available in the memory stage and not in the execute stage as in all other instructions. For branch prediction, we have always taken. And the address of the program counter like of the that the branch predictor gives you becomes available after the decode stage. Yeah, you can assume internal register file forwarding. An instruction writes into a register in the first half of a clock cycle, and then another instruction can access the same register in the next half of the cycle, and the compiler does not reorder any instructions that you get. So this is the piece of code that you are given. Before trying to break it down into stages, I'm going to calculate how many loop iterations are going to get executed here. So the loop condition is that you're going to branch and not you're going to branch back here essentially when 1 and 5 are not equal. So register 1 and register 5. Register 1 starts with a value of hexadecimal, whatever this is, and this is the value of register 5. The difference between these two is 16, because that's what you get when you subtract these two values. And you can see that we increment the loop counter by a value of 4 each time, which is held in register 1. So that means that 16 divided by 4, you're going to have 4 iterations of this loop. 4 loop iterations. Let's write this down. There is also a different branch inside the loop, which is based on the values that are held in these memory addresses. And this is going to influence how long our program takes to execute. So I'm going to, before doing anything, to see what is the direction of this loop. So you can see that the program begins by loading the value that's held in the address containing register 1 to register 2. And then it's going to do an AND operation on this value with the binary value of 1, and then it's going to branch on this value. So essentially, the value that it branches on here is containing this memory address, this memory address, this memory address, and this memory address for each loop iteration. And this is the actual value in all these cases. So for the first 3 iterations, these are even numbers. So the result of this is going to be 0, the result of the AND-I operation. And that means that you're going to be branching here for the first 3 iterations. First 3 iterations. And then for the last iteration, this is a not value. So you will have to go through these instructions as well before continuing forward. This is going to happen for the last iteration. And I'm going to write down here branch taken for first 3. Not taken for last iteration. So let's see what happens now when you go and actually execute these instructions. Where's my trusty ruler? Yeah, sure. Thanks. I'm going to distinguish between 2 cases, which is one where the loop is the branch is taken, the first branch is taken, and the one where it isn't. So we have. Yeah, sure. Okay. This is where the branch is taken. I'm going to write taken here. So AND-I branch And then the next instruction is going to be the addition. And the last one is going to be the loop condition, essentially, branch not equal. So we're going to have sorry. The other way. Ah, okay. Yeah, cool. Fetch, decode, execute, memory, and write back. And then fetch, decode. Here, there is a dependence between the register 2 being loaded by the load instruction and NDI using this value. So you have to stall here. You have to put a bubble in the pipeline. This is going to execute now. Again, memory and write back. The branch and equal instruction, again, it starts over here. Fetch, decode. There is a dependence again. So you have to put a stall here. Memory and write back. Because this is a branch, the next PC is going to be decided after this stage. So you can fetch here, not here. Fetch, code, execute, memory, and write back. Okay, we're going to need some more of that. And this is the loop condition checking. So we can fetch here, fetch, decode, execute, memory, and write back. After this, the next loop iteration is going to happen here, which is going to be another load word instruction. We don't care about this right now, but this means that as long as this keeps executing, you have to charge from here to here 1, 2, 3, 4, 5, 6, 7. Yeah, 7 cycles. You have to charge 7 cycles for each loop iteration. And then if this kept happening at some point and stopped, you would have to add another 3, the ones that are in here. Now I'm going to take the second case, which is that we have extra space, it seems. The branch is not taken. So here again, we're going to have actually, let's do this so that you can also see the program. And now these instructions are also going to get executed, the ones that are in between. So you have, however, before that, the branch predictor is going to fetch the predicted instruction, which is going to be again a die. So let's go and start executing, because then we can see when it's going to roll back to the correct state. fetch, decode, execute, memory, write, fetch, decode, stall, execute, memory, write back, fetch, decode, stall, execute, memory, write back. Branch prediction here. So this is when you're going to fetch the ADA instruction. However, you're going to decode it as well. And at this point, the processor is going to realize that it has fetched something wrong because the execution state of the branch instruction completes. So there will be no further pipeline stages for this instruction. And it's going to fetch the correct instruction, which is this load word over here. So load word over here, when exactly after the execute stage. So here, this is how it goes. Fetch, decode, execute, memory, write back. After that, the next instruction is add. So add, fetch, decode. The add has a dependence to the value that is loaded over here. So you have to put a stall here, and then you can execute it. And the next instruction after that is add, add I. There are no dependencies, so fetch, decode. You cannot execute here because the execute stage of the pipeline is occupied. So you have to put a stall there. And the last instruction is going to be the branch not equal. Fetch, decode. Again, this is occupied, so you have to put a stall there. Execute, memory, and write back. And again, because this is there is a branch predictor in here, it would continue fetching the next instruction because it's predicted after here. Even though the program is finished, essentially, it would fetch the load word instruction from the top here. However, it's going to get resolved before this completes anyway. So nothing else is going to happen. The program will terminate at this point, and you don't have to take this into account when calculating the total cycles in the end. So let's calculate the total number of cycles for this, for this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 cycles. So we had 7 cycles for each time the first case is executed, which are 3, as we said in the beginning, and another 15 for the last one. So this will give you 21 plus 15, 36 cycles total. Good. Okay. So the above code, what you just saw here, was generated by the following C code, which is this for loop. There is an if statement, and then you do something on the value held in the result. You add B of I, essentially. You have to rewrite the code using a multiplication to eliminate the if statement. And what it's going to do is that it's going to take all these things that happen with the branch prediction over here and throw them away because you're eliminating that if statement. And the trick that you have to realize in this case is that you can see that basically one way to completely avoid the if statement is to multiply the value of b of I by the result of this operation, because it's going to be either 0 or 1. You are doing an AND operation with a value of binary 1, so it can only be 0 or 1 in that case. So for result gets incremented by A of I, which is ANDed with always difficult to write down, and you're going to multiply this by B of I. Now, when A of I is 0, for example, when it's 0, yes, this is also going to be 0. So it has exactly the same effect. I shouldn't say even 0. I should say an even number. And when it's an odd number, it's going to get multiplied because this is going to be 1, and you have exactly the same effect. So based on this C code that you have over here, you should write a new optimized assembly code segment that experiences no data dependencies. So this is possible to do, and for that, you're going to need some help for your like the initial assembly code that you got, so you don't have to become a compiler yourself. And you're going to start by doing load word. You have to, yeah, sure. Actually, we don't need this anymore, so we just need these now. You're going to fetch the value of B of I, of A of I, excuse me, which is, yeah. Then you're going to do a trick, and because you will have to do an AND operation of A on A with with 1. If you did it right here, it would cause a stall because the value is not ready. It's a load dependence. But you know that you need to fetch the value of B anyway because this will get executed all the time. So you are going to issue a load instruction again for the value of B this time. And this is going to be and now you can execute the AND operation without any dependencies. This corresponds to this thing over here. And then you have the multiplication instruction that we inserted to do this trick. You're going to multiply into register 3 the value contained in register 2 and register 3. You add it to the running sum, which is this result variable over here, and register 4 in the initial example. And then you also increment the loop counter. So which is held in 1, you increment it again by 4. This is exactly what it was in this. These last instructions actually are exactly identical to what you had in the beginning. You don't have to do any changes for that. And then there is going to be the loop condition, branch not equal. Loop here. So let's see how many cycles this takes to execute in total. Okay, provide the total number of cycles it takes to execute the new code. Show your work. So we start with a load word. Fetch, decode, execute, memory, write back. Another load word after that, there is no dependence between the two. They operate on completely different items. Then there is going to be an AND-I operation between the values of these two loads. Fetch, decode, execute, and there is going to be forwarding from here to here without any stalls. Why? Because we said that assume internal register file forwarding, an instruction writes into a register in the first half of a cycle, and another instruction can access the same register in the next half of the cycle. And also, you can forward an operand from the memory stage to the execute stage. So that's why you can do this forwarding over here. And the next step is the multiplication instruction. Fetch, decode, execute, again, forwarding from here to here. Memory write back. You add this to the running sum. So fetch, decode, execute, write back. You increment the loop counter. No dependencies here because this value is never affected by anything else or fetched anywhere. And finally, the loop counter. Fetch, decode, execute, memory, write back. Again, you might be fetching the next iteration here. So I'm going to put an F here because we will need this to calculate how much time an iteration takes. You're going to need 1, 2, 3, 4, 5, 6, 7, 8 cycles when the for each of the 3 initial iterations of the loop, and you're going to need also 8 plus 1, 2, 3, 11 when for the last iteration of the loop, when this also has to get executed, so that all the instructions are executed completely. So 3 times 8 for the first 3 iterations plus 11 cycles. This gives you 24 plus 11, 35 cycles in total, which is 1 cycle less than what we needed for the non-optimized code segment. Do you have any questions? Okay, I think in that case, we can probably move on. You're next? Cool.
Okay, I hope you can hear me well. Good. Yeah, it's green. Okay. All right, now, good? Okay. Now we will do some virtual memory questions. This was covered like fairly more recent in the lecture, so maybe you remember it more than previous topics. So like we have a set of multiple choice questions. The first question mainly about the primary purpose of a translation look-aside buffer. So as we recall from the lecture, a TLB is a small and a fast cache that we use to basically store the recently used virtual to physical address translations. So the idea is if we hit in TLB, we look up the virtual address and we immediately get the physical address, right? So we don't need to go to the page table. So basically this, of course, accelerates the whole process of virtual to physical address translation, which we see here in option B. So here, this would be the correct answer. If we need to go through the other options, A, to store the entire page table and enable fast lookups, we do not store the entire page table in TLB. C, to store recently accessed data from main memory. This is more the definition of a cache. And D, to manage the swapping of pages between physical memory and the disk. This is something that OS handles, and it's not about TLB, basically. So the answer here would be B. If there are no questions, I will move on to B. Here we have a system with 32-bit virtual address space and a page size of 4 kilobytes. And the question is, how many entries would a single level page table require? So to find this out, we basically need to divide the total bytes of the virtual address space to the size of a page. So we know that the virtual address space has 32 bits, meaning the total bytes we have here is 2 to the power of 32. And the page size of 4 kilobytes basically mean 2 to the power of 2 times 2 to the power of 10 bytes, meaning 2 to the power of 12 bytes. So size of the virtual address space divided by the size of each page itself, it gives us 2 to the power of 20. So this is the number of entries we would need to have for a single level page table. So the answer here would be C. Any questions? Okay, then we can move on to question 3. Which of the following is a primary advantage of using virtual memory? A, it allows the physical address space of a process to be non-contiguous. B, it guarantees that a process will never run out of memory. C, it allows a program's logical address space to be much larger than the available physical memory. and D, it completely eliminates the overhead of address translation. Do you have a guess? Yes, exactly. So basically, as a programmer, we get this illusion that we have way more memory than we actually do. And that's why we use virtual memory. Maybe Spiros can tell you more about that later. If it's more related to ISA or microarchitecture, like yeah. Yeah. But yeah, it's good to think of questions, I guess, to prepare. Yeah, so I guess the other options are clear why they're not. Like eliminating overhead of address translation is quite contrary. You introduce that. We'll never run out of memory. That's not correct. You can still run out of memory. And a process being non-contagious is more like an attribute of paging and not directly for like primary reason for virtual memory. Okay, I'm moving on then to question 4. A page fault occurs when A requested page does not reside in physical memory, but in the hard disk. Basically, if you recall from the lecture, there are 2 types of page faults, minor and major page faults. And the scenario we have in A would be a major fault. Basically, it indicates that the virtual page is not in the memory. The OS handler raises an exception to move the data from the disk to the memory, and this takes quite some cycles. So this would be a major fault. B, a requested page does not reside in physical memory, does not reside in the hard disk, and is not yet mapped in the page table. This is also a case of a minor page fault. In this case, like I think in the slides, there was this scenario where you do a malloc and you want to access, but no mapping has been established yet. And in this case, the OS would do a page table walk and it will just install this to the page table entry. So this is also a case of a minor fault. And C, a requested page is already in physical memory, but is not mapped in the page table of the requesting process. This is also another scenario for a minor fault. Happens, for example, when 2 processes uses the same shared library. And in this case, again, the OS installs page table entry. So all of these are different scenarios where a page fault might occur, meaning the correct answer would be D, all of the above. Okay. Then we move on a bit to TLB and page table walkers. We have a similar question here. Now we need to consider a system with 64-bit virtual address space and a page size of 4 kilobytes. And the question is, how many bits are used for the page offset and how many bits are used for the page number? So basically, page size of 4 kilobytes, again, means 2 to the power of 2 times 2 to the power of 10 bytes, so 2 to the power of 12 bytes. And basically, to be able to address every individual byte inside the page, we exactly need 12 bits for the page offset. So here we would need 12 bits for the page offset, and all the, like, since we have a 64 bits virtual address space, all the remaining bits, meaning the 52 bits would be used for the page number. Yes. Yeah, it's more like more of a straightforward question that you just need to know how to map them correctly. Okay. And question 2, for the previous system, do we need to translate all 64 bits of the virtual address? Do you have an answer for that? Maybe. No. So basically, we do not need to translate all the 64 bits because we don't need to translate the page offset. We just need to translate the page number. So no, we only translate the page number. Yeah, because the ordering within the page offset doesn't change anyway, so there's no sense of translating it. Okay. And moving on to question 3. Consider an L1 TLB that stores only 4 kilobyte virtual to physical mappings, has 1024 entries, and is fully associative. Provide the maximum amount of memory that the L1 TLB can cover. Basically, what we need to do here is that we need to, okay, we know we can store 1024 bits, so we need to multiply the number of entries with the size of the mapping, basically. So in this case, we would multiply 1024 entries with 4 kilobytes. So 2 to the power of 10 times 2 to the power of 12 bytes equals 2 to the power of 22 bytes. And basically, this means 4 megabytes. So this is the amount of memory that we can cover the given conditions. Question 4, moving on if you don't have any questions. Now we consider a TLB that stores both 4 kilobytes and 2 megabytes virtual to physical mappings. So an entry can be either a 4 kilobyte or a 2 megabyte entry. Now we have 2048 entries, and it's fully associative. Now we need to find out the minimum and the maximum amount of memory that the L1 TLB can cover. So for the minimum amount of memory, basically we would consider a case where all of our entries are 4 kilobyte mappings. So in that way, we would basically cover the least amount of memory. And in this case, we would, again, using the same formula as we did in question 3, multiply this time 2048 with 4 kilobytes. So 2 to the power of 11 times 2 to the power of 12, 2 to the power of 23 bytes. And this equals 8 megabytes. And for the maximum amount of memory that we can cover, now we calculate basically assuming that all our entries are 2 megabyte mappings. And in this case, you would have, so the megabyte is 2 to the power of 20, so 21. So this is now, this is gigabytes, so 4 gigabytes. So yeah, this is the minimum amount, that's the maximum amount, and every combination in between is also possible. Okay, and question 5. How does the size of the virtual to physical mapping entry affect the hit to miss ratio of the TLB? And explain your answer. So let's say, for instance, when we go from 4 kilobyte mappings into 2 megabytes mappings, how does this affect the hit to miss ratio of the TLB? Like, I think like intuitively, you can already guess if we have 2 megabyte entries, we're covering for more memory, right? So the chances of us getting a TLB hit for the virtual address that we want to map is going to be higher. So it increases, meaning as size of virtual to physical mapping entry increases, the hit to miss ratio also increases. Since we cover more memory with the same number of entries. Okay, question 6. Mention one advantage and one disadvantage of using a software-based page table walker instead of a hardware-based one. So basically, one advantage of doing the page table walk in software is the fact that we would have more flexibility. Like, for instance, we can use different page table structures for different processes, like radix trees or hashed page table entries. So we have more flexibility in general in software. But a disadvantage is that this, of course, causes to like a higher latency because the OS overhead of raising an exception and the context switches basically increase the amount of time that this process is completed. So the advantage would be more flexibility. And the disadvantage is that it's slower than hardware-based one. Due to context switching overhead. Yeah. Okay, do you have any questions on this part? Yeah. Mm-hmm. That is true. That's like one trade-off, yes. So in general, you would spend more time loading the 2 megabyte pages, but your ratio would be higher. You would hit more. Yeah. And like this trade-off might make sense for some applications and for some it might not. And yeah. I definitely think it changes. It's a whole big research topic. Yeah, that seems. Okay, then I would move on to the next question, alternative address translation. So basically, we have the following scenario here. We find out that for some specific virtual memory regions, we experience a high address translation latency because we always keep missing in the TLB hierarchy. And to mitigate this disadvantage, basically, we decide to add an additional address translation path that can perform quick page table walks for this specific virtual address ranges that we had observed cause TLB misses. And to make this happen, basically, we come up with this following scheme. We say, if the virtual address is in this range, then we're just gonna add this offsets to get the physical address. And also the following for this three ranges that are given. And what we need to do is that we need to design a circuit for the new memory management unit that includes both the circuit that figures out whether the virtual address is within one of these three ranges. And if so, a new page table walker that performs this offset-based address translation. And we can use the following digital circuits and so on, comparators, registers, others, and so on. So basically, how would our memory management unit look like? So we get a certain virtual address, right? And the first thing we do, like what we have in the memory management unit, are the TLBs. So we most definitely are gonna do a lookup into the TLB. In most cases, we have both for 4 kilobytes and for 2 megabytes mappings. So we're gonna do our standard lookup. This is already a part of the memory management unit. And if it's a hit, great, we get the physical address. If it's a miss, then what we do is that we go to our standard hardware page table walker. This is already like the existing scheme that we have. So what we want to build on top of this is that additionally, we want to identify whether the virtual address lies in one of these three regions. So we need to somehow, first of all, okay, so we get the virtual address. We need to first of all, like basically compare whether it lies in any of these three ranges, right? So we can start with the first one. We want to compare whether the virtual address is within this range. And for this, we need to store the lower and the upper bound inside a register. And we can use a register, great. So we can store basically the first lower bound here in the register 0, and then the upper bound in a register 1, let's say. And we need a comparator, right? So we wanna, so if this virtual address is larger than the lower bounds, so here we put greater than comparator, and the virtual address will be one of the inputs, and the value here is gonna be one of the inputs, and we're gonna have an output. The same scenario here for the upper bound. This time we're gonna have smaller than comparator. And we also need the virtual address as an input, because that's what we're comparing with. Basically, if both of these conditions are true at the same time, then we want to add then we say, okay, it lies in this first range, and we want to add this physical offset, right? So both conditions being true, meaning we need an AND gate here. And if the output here is a 1, then we say, okay, we're just going to add this physical offset. And we're going to basically do something with this output. For now, I'm leaving it open. So this kind of checker we need for all of these virtual address ranges. So we can easily do the same for the following. So in R2, we can store 0xFF000 in, and then 0xFFFFF in R3. Again, the two comparators. Take the output, put it into an AND gate, and then for the last condition, R5, comparator, input, another AND gate. Okay, sorry for my crooked drawing. Yeah, so if basically one of these conditions are true, then we wanna not follow our usual path, but we wanna basically go to our modified page table walker where we're gonna add the physical offsets, right? So we kind of need a gate here that differentiates between like all the outputs here being 0, 0, 0, and even like, and just like that the fact that one of them is gonna be a 1 is gonna change the output of the gate. So here basically we can use a NOR gate. And I think an OR gate would also work. So basically here, if all of them are 0, then we get an output 1. And even if one of them is 1, we get the output 0, right? So we can differentiate whether the virtual address is one of these in these ranges. And if that's the case, then we go to the modified page table walker. In the sample solution, this is like the way that it looks like. So I don't think you're required to also draw how the modified page table walker would look like. But I think it can be a fun exercise like for you to try. And like as a tip, the idea would be to basically, we would need a multiplexer. We can use these outputs, these conditions as a select signal to figure out which of the physical offsets that we want to get as the output of the mux. And once we have that offset output of the mux, we can feed this into an adder. And the input to the adder would be the virtual address. So you would just add both of these, get the physical address immediately, and then we can add another mux where, depending on this output, we know whether the physical address should come from the page table walker or from the modified page table walker, because it's going to be way faster. And if it's enabled, then we see that this is the case, then we get the physical address output faster, single cycle latency. Yes, that's the idea of this question. Do you have any concerns or like parts that were not clear? Yeah. Right now, it's a bit more like left a bit more high level in the sample solution. But what I meant was that because like anyways, we want to follow our usual path. But just in case if the virtual address is one of these ranges, it's going to be detected way faster. And it's going to go to the modified page table walker way faster, right?
Yeah, but if I understand it correctly, so what you draw is that you're in one of the three interesting cases
Mm-hmm.
that you get a data bit, right, that says we are in those cases.
Yeah.
And so you just connect it
Yeah, which essentially would be like a more complicated adder, right? Like where you have a bunch of muxes, like I'm. Yeah, definitely, definitely. You're right. So yeah, it's also not driven in the sample solution, but most definitely, like here, there would be a virtual address input for sure. Yeah. Okay. Okay. You don't have more questions. I would move on to the next part, which is going to be about caches. Okay. Okay, so we know that a computer uses 32-bit addresses and 32-bit data. Its L1 data cache is a byte addressable 16 kilobyte structure of 512 blocks, two-way set associativity, write back, and least recently used replacement policy. And we consider a code fragment, like given here, where A, B, and C are vectors of 4 bytes integer elements with addresses given. And what we want to figure out is that starting from an empty cache, what is our L1 data cache miss rate gonna be while we're executing this code? And show your work. So basically, to be able to calculate what our cache miss rate is gonna be, we first need to know how we're gonna map these addresses into the caches, right? So we need to figure out some things about the cache first, but that's why basically we have all these properties of the cache given. So we know that it's a two-way set associative cache, and we have 512 blocks. And if we recall from the lecture how a set associative cache looks like, basically we're gonna have, let's say, a set 0, and it's two-way, so we store 2 blocks inside one set, right? And then we're gonna have a set 1, where we have also 2 blocks, and so on. So we first need to find out, basically, given an address, how many bits do we need to address the tag, the set, and the offsets in the cache. So starting from the offsets, we know, like, to find this out, we basically need to divide the total size of the cache into the number of blocks. So we know it's a 16 kilobyte cache, and we divide this into 512 blocks. So 2 to the power of 4 times 2 to the power of 10 bytes divided by 2 to the power of 9. We get 2 to the power of 5. So 32 like bytes per line. So we know that's in each line, meaning block. So we know that in each block, we store 32 bytes. And basically, to find the offset bits, we need to find out how many bits do we need to be able to address the 32 bits. And that's exactly why we do the log 2 of 32, and we get like the 5 bits for the offsets. So we need 5 bits to find out within a block where to look at. We can also find out how many bits we need for the set. Since we know we have 512 of these blocks, and we know we have always 2 blocks per set, right? So we can just divide 512 blocks into 2, ways, and we get 256 sets. So knowing we have 256 sets, this means we need 8 bits to address the set. So 5 bits here, 8 bits here. In order to find out the number of bits required for the tag, we can just, so we knew the computer uses 32-bit addresses, so we can just subtract 8 and 5 from 32. And we get 19. That's basically the first thing that we need to do for this question, so that we can then go back to the given addresses for A, B, and C and find out how they're going to be structured inside the cache. Okay. So let's visualize this a bit. So we have the address A, B, and C given. We have a tag here for the first 19 bits. So we see for all of them, the first, here we have 4 Fs. So the tag is gonna be 1111, 1111, 1111. So 4 times the F. And then for A, we have a 0. So here we already have 4, 8, 12, 16. So we have 3 bits remaining, right? And we have a 0 here, so 0, 0, 0. And that's it. And the next one is also going to be 0. For B, we have an 8, so 1, 0, 0, and 0. For C, we have an E, meaning 1, 1, 1, 0. So this is the, so we see, okay, we have different tags for A, B, and C. We now can decode the set. We know we need 8 bits for it. So as you can see for A, it's completely 0. 2, 3, 4. For B, also 0. For C, we have an 8. So 1, 0, 0, 0, and then 0 again. So 8 bits for set, and then the remaining offset bits are all 0. Okay. So what we can do now is, okay, we already see A and B both have the same set bits. What we can do now, so we want to figure out basically how much of the vector we can store in one block. We know that we can only store 32 bits per block. And we know that one integer, like that our vectors have 4 byte integer elements. So we can divide this by 4 bytes and get the 8 vector elements per cache block. So like, let's say starting from A of 0, we can store all the way up until A of 7. Okay, so now we can observe basically the code fragments a bit more here. Maybe before that, I can already draw how the cache would look like. So sets, we have the lines, and we have the content for the blocks. Like I mentioned, A and B both set 0. And do you think it's a problem? Okay, we're gonna see it now. In this case, no, because it's a two-way set associative cache. So we will have space for both. So let's say we start executing the program. I equals 0. We want to access A of 0. We look up, we go to the set, we see that it's not there. It's a compulsory miss because it's the first time that we're accessing, so it's fine. But it's gonna be a miss, basically. It's gonna be a miss, but we're gonna bring the contents to the block here. We're gonna bring A of 0 up until A of 7, because that's the maximum amount that we can start. That's what we had figured out here. Then we continue. We want to access B of 0 now. We check the sets and we can't find B. Again, a compulsory miss. But now we have space in the cache because it's two-way. So we bring B here in the same fashion. So we have A and B now. Plus, we want to access A of 0 again. We go up, and this time it's going to be a hit because it's in the cache. It's A of 0. Then we want to fetch C of 0. Looking at the address mapping for C, we see that this 0, 1, 2, 3, 4, 5, 6, 2 to the power of 6 is 64. We go to set 64. Basically check the tag and we see that C is not there. This is again a compulsory miss. So we bring in C here to set 64. So miss on C of 0. And we compute this, and then we want to write back into C of 0. And this time we hit. Yes. So that's the first iteration for this giving loop. And for all the next 7 iterations that we know that the contents are in the block, the following is going to happen. So we increment I. I equals 1 now. We want to access A of 1. We go to set, we compare the tag, we see that A is here inside this block. So A is gonna be a hit each time. B, same way, it's always gonna be a hit. And then we're gonna access A again, a hit. C, again, nothing is evicting anyone, so hits. And also for writing back, it's gonna be a hit. So this is an ideal scenario where the only misses are basically compulsory and nothing is evicting each other. So these basically are all memory accesses. So in total, we have 8 times 5, so 40 memory accesses. And out of these 40 memory accesses, how many misses do we have? 1, 2, and 3. And that's it. All the other accesses are hits. So miss rate equals 3 divided by 40, which is 7.5%. And yeah, just doing this is enough because basically for the next elements, the same analogy. Next time, the same thing is gonna happen in sets 1 and set 65 for C and so on. So it's the same scenario. Okay, do you have any questions? Okay, then I'm moving on to the last question. This is more like a follow-up. What if the vector C starts at this address? We need to basically recalculate the new miss rates. So if we decode this address, we see the following. The tag is the same as we had before. But what happens now is that the set is also 0, just like A and B. Okay, so this should already be, it should already be clear that this is an issue, right? Because we have the same sets for both A, B, and C, but we just have a two-way set associative cache. If we had a three-way set associative cache, then all would be fine. Like the hit rate, the miss rates would stay the same because we would have space here also for C, but now we don't. And so basically what happens is that, so if we follow the same approach, we have for I equals 0, we bring in A like we did. We have the compulsory miss. We bring in B, again, we have the compulsory miss. We hit A, we find it inside this cache. And when we look up C, we basically look up again to set 0 and we find out it's not there, but both of the lines are occupied. So what we need to do here is that we need to evict the least recently used data, which in this case would be B, because we just accessed A. So now we need to evict B and overwrite this with the data of C. So we would miss on C again. And basically, yeah, we would just have C and A here. And when we need to write back, we hit again because we just overwrote B and brought C. So miss C, hits C. But what happens in the following iterations is that when we start with A, again, it's a hits always, because it's always the most recently used. But instead of hitting on B, like we did before, we're never gonna find back the data for B. This is always gonna be overwritten by C. So each time we're gonna miss on B. A is gonna be a hit, like I mentioned. And for C also, because now we accessed B and we overwrote C with B, we're not gonna find C here anymore. So also C's are gonna be a miss for the first access every time. And when we write back, this is gonna be a hits again. So in this case, C is always gonna evict B and B is always gonna evict C because we simply have a two-way set associated cache and all these addresses, they're mapping to the same set always. And again, out of 40 accesses, so in the first iteration, we have 3 misses and then 7 times 1, 2. So 17 misses, meaning our new miss rates is gonna be 17 divided by 40, 42.5%. So as you can see, it's very visibly worse compared to what we had before. Yes. Do you have any questions? Okay. If not, I think I would. Architecture next. Okay.
I'm audible now. Okay. So yeah, next we will solve the performance evaluation question. Let's first start with reading the question. So in the question, we are said that a multi-cycle processor P1 executes load instructions in 10 cycles. So we are given the latencies in cycles of different types of operations, and then the store instruction in 9 cycles, arithmetic instruction in 3 cycles, and branch instruction in 4 cycles. Now we have to consider an application A, and we are given the breakdown of how much instructions of each type does that application have. So we have 30% of load instructions, 10% are the store instructions, and 40% of all the instructions are arithmetic, and 20% are branch instructions. So now in the first part, we have to calculate the CPI of application A when executing on processor P1, which is the one that we are told here. And we have to show our work. So I think most of you know that CPI is cycles per instruction. And in this case, we care about the average CPI. So basically, we mostly like simply multiply and add the number of cycles taken by each instruction and the number of instructions that we have. So here, like here, we have 30% of all instructions are load instructions. So 0.3, and load instruction takes 10 cycles. So we will do into 10 plus, then 10% of the instructions are stored. So we do 0.1, and store instruction take 9 cycles. So into 9 plus 40% are arithmetic, which takes 3 cycles, and 20% are branch, which takes 4 cycles. So we just have to do the math, and if we do that, we will get around 5.9. So this will be the answer for this part, the CPI of processor 1. Okay. So, okay, now next move to the next part. So here, we made a new design of the processor, which has double the clock frequency of processor P1. However, the latencies of load, store, arithmetic, and branch increase by 3, 2, 1, and 1 cycles. So this new processor we call P2, and the compiler used to generate instructions for P2 is the same as for P1. So the number of instructions that this processor will produce would be the same as P1. So now we have to tell the CPI of application A, again the same application that we did in part 1, when it is executing on processor 2 instead of processor 1. So we again do the same thing. We calculate the CPI. The number of instructions are same, but we like increase the cycles. So for load instructions, the cycles increase by 3. So it would be 10 plus 3 here. Plus now the store instructions. So the cycle increase by 2. So 9 plus 2. Then arithmetic instructions, 3 plus 1, as we have increased by 1 here. And then branch instructions. Here we have 4 cycles plus 1. So again, we do the maths, and if we calculate this, we get around 7.6. So this is the CPI for processor 1, and this is for processor 2. So I hope everything is clear till now. In the next part, we are asked which processor, P1 or P2, is faster for the same application A, and by how much, and we have to show our work. So we can simply calculate the execution time of both the processors and compare. And the execution time is the number of instructions into CPI into 1 by clock frequency. So let's first calculate the execution time for processor P1. So now in the second part, it was written that the compiler used to generate the instruction for P2 is the same as P1. Thus, it produces the same number of instructions. So let's assume the number of instructions are I. In both the cases, it would be the same. So we can just simply write I here. And now the CPI for processor 1 is 5.9 as we calculated here into 1 by clock frequency. Let's assume the clock frequency is F. So this is the execution time for processor 1. For processor 2, number of instructions remain the same as I explained. And the CPI for processor 2, which is 7.6. And 1 by clock frequency. So here we have that the clock frequency is double for processor P2. So 2F. Now we can simply take the ratio of these execution times. This just cancels out. This cancels out with this. So we have like 2 into 5.9 by 7.6. 3.8. So if we move the terms there, so EP1 is equals to 5.9 by 3.8 into EP2. So this term is greater than 1. That means execution time of processor 1 is greater than execution time of processor 2. So that means that processor 2 is faster. And we can divide them to get by how much. So it will be like nearly 1.55 times faster. Okay. Any questions still here? Okay. Then let's move to the last part of this question. Yeah. So here we are said that there is some extra area available in the chip of processor P1, the one we were talking in part A, where extra hardware can fit. So you can decide to include in your processor a faster branch execution unit or a faster memory device. The faster branch execution unit reduces the latency of branch instructions by a factor of 3. And the memory device reduces the latency of memory operations by a factor of 2. Which design do you choose to run application A that we are talking all along? And we have to show our work. So there are 2 ways to do this question. So first is the very simple way, as we are doing by calculating the CPI. So first of all, let's see how much memory instructions we have. So memory instructions are load and store instruction. So 30% are load and 10% are store. So basically we have 40% of all instructions as memory instructions. And for the branch instructions, we have 20%. So 20% of all are branch instructions. Okay. So now if we calculate the CPI again, so in this case, we are asked for processor P1, which is this one. So we have to use this. So CPI new would be, no, CPI in the case like new when we have like memory instructions. So in the case of memory instructions, we will say 0.3, which is load, and for the memory operation, it is latency is reduced by a factor of 2. So earlier it was 10 cycles, now it would be 10 by 2. Similarly, for the store instructions, it would be 9 by 2. And for the others, it remains the same. So that is 0.4 into 3 plus 0.2 into 4. So so we can calculate this, and once we calculate this, we get around 3.95. Similarly, we can calculate in the case of like branch instructions. So in this case, this thing remains same. Arithmetic also remains same. And for the branch, the cycles are, the latency is reduced by a factor of 3. So we will have 4 by 3. So this CPI in case of branch would be around 5.37. So now we can see that CPI in case of branch is greater than CPI in case of memory. And here by this formula, we know that like we can also substitute CPI here, but we can also see that generally execution time is proportional to the CPI, directly proportional, and the clock frequency for one processor is the same. So execution time would be more in the case if we have a faster branch execution unit than the faster memory. So that means we will choose a faster memory device. Is it clear? Okay. So this was approach 1, let's say. We can also solve this question alternatively by applying Amdahl's law, which is so the formula of Amdahl's law is 1 minus 1 over 1 minus p. So you can say p is the portion that we are enhancing. So for example, branch or memory, plus again p, the portion that we are enhancing, upon the speed up that basically enhancement is giving us. So in the case of memory, so this is equal to speed up. So speed up in case of memory would be 1 upon 1 minus, so for P, the memory instructions were 40%. So 1 minus 0.4 plus 0.4 over the speed up that we get in the case of memory 2. And similarly, the speed up for branch we can calculate, which would be 1 by 1 minus 0.2 plus 0.2 over 3. So from this, by solving the math, we will get that the speed up in case of memory would be greater than speed up in case of branch. So here we again lead to the same observation that we will choose a faster memory device. So that was about the performance evaluation question. Do you have any questions? Okay. So next is the VLIW and instruction scheduling question. So this is a bit like lengthy, but these are all the instructions that will help you in solving the question, and it's like you don't need to worry about it. So we can like read the question together. So it says that you are the human compiler for a VLIW processor whose specifications are as follows. So there are total of 6 functional units, 2 of which are load units, 1 store, 1 addition, 1 multiplication, and 1 branch unit. And then it says the VLIW processor can only execute assembly operation listed in table 1. So this is the table 1. So we have some instructions listed here. First is the load. So we have 2 types of load instructions. First is simple load instruction, and second is load increment. So this is the instruction, and these are the semantics, how those instructions work. So for load, we will have a destination register, 2 source registers, and an offset. And how it works is that, so first we will take the content of source register 1, source register 2, add them, and then add them with the offset. And this becomes our address, and we fetch the data from this memory address and basically load it into the destination register. For load increment, also, this part is the same. We just increment the source register by 1 after we have like loaded the data. So this is about load. Similarly, in the case of store, we again have 2 source registers, offset, and basically in this case, the destination register is called source register 3. It's the same thing as this. So here we have to get the data at this source register 3 and store it at this memory location, which we can like get by adding the 2 source registers and an offset. And similar to load increment, we have store increment. After storing the data, we increment the source register 2 by 1. Next, addition. So we have 2 source register, destination register, and we add the contents of 2 source registers and like basically store it in the, get it in the result in the destination register. Similarly, for multiplication, we just multiply instead of adding. And next is the branch. So in branch, it's called BNE, and the registers we have is the source register, and then we have an offset, and then we have a target. So how it works is that branch to target if source register 1 is not equal to the offset. So it basically helps us to loop to check if the value of source register is equal to the offset, and if it is, then it branches to the target, otherwise it just keeps on going. And these are the 5 useful instructions that we have. And the last is the like NOP, which is no instruction. So in this case, the functional unit is idle for 1 second. So that was about table 1. And I already explained to you what is written here. The table shows the instructions that each functional unit can execute and each instruction semantics. Note that the load increment and store increment instructions automatically increment the address source register are source 2 by 1 after data is loaded or stored, as we saw here. So this was the second point. Third point is that all assembly operations have a 1 cycle latency, including load, load increment, store. So for example, here we are executing 2 things, so it still takes 1 cycle for both of the things. Next, the machine has 32 registers, R0 to R31. The registers are read at the rising edge of the clock and written at the failing edge of the clock. And the memory is word addressable, and 1 word is 4 bytes. Next, the power consumption of a functional unit when executing a useful operation is 5 watt. And what do we mean by useful operation is that all these assembly instructions like load, store, addition, multiplication, branch. And this NOP is not a useful instruction, and the power consumed in this case is 1 watt. And the VLIW processor operates at 1 gigahertz. So these are some of the instructions that we should know. Okay, so next we are given figure 1, which is this. It shows the C code and its equivalent assembly code for the application that we will execute in the VLIW processor. So let's assume n is an even positive integer throughout this question. So this is the assembly code. So here we have 4 integer arrays, which have n plus 1 number of elements each. Then here, let's assume that the arrays are initialized. So now next we run a loop for I is equals to 0 till I is less than n. We add the contents of like add element by element, the elements of array A and B, and then multiply the result with the elements of array D. And then this complete result is stored in an array C. This is the assembly equivalent of this C code. So before going to the assembly code, we can read this. So in the assembly code, registers R29, R30, R31, and R28 hold the base addresses of the C code arrays A, B, C, and D respectively. Register R0 is initialized with 0, and register R1 is initialized with 1. So now let's understand the assembly code. So first of all, we have to do AI plus BI. So first we have to load the element from array A, and array A is at the like register R2, as we have mentioned here. So we will, so as we here, we can see the semantics of load. So if we take the first source register, which is R29, which stores A, then second source register, which is R0, like we are said, it is initialized with 0, and n is also like our I is also initialized to 0. So basically we can say that this register stores the value of I, which we have to increment after each operation here, full operation. And we have to fetch the element from offset 0. So this will load the element at index 0 of array A in R2. And similarly, we will load B1, which is at register R30. So that's why we have R30 here instead of R29. So once we have loaded the elements of array A and B, we can add them. So then we have add instruction. So these are the basically input registers, we can say, which stores the value of A and B. And we store this addition, the value we get after addition in register R4. Now we got this value in R4. Now we have to load D1 because we have to multiply the result of A plus B with D. So D is at register R28. So similar to these two, we just now load it from R28 because it stores D, and it is loaded into R5. So now we have value of basically A plus B, the first element, I'm only talking about the first element, in register R4, and the value of D in register R5. Now we can simply multiply the value at R4 and R5. So if we do that and we store that value at basically register R6. So this is the final result that we get after adding A, B, and then multiplying with D. So we have to store this final result. So we have to store in C, and C, the register corresponding to array C is R31. So here we store at R31 and we store the value of R6. So this is the store instruction. So once we have done that, we have to now loop and we have to run this code until I is less than n. So we break this loop when the value of R0 and n are equal. Otherwise, we'll just loop. So is everything clear in the question? Okay. So let's start with part A. So here we are said that your goal in this question is to statically schedule the instructions in figure 1. That was the C code and assembly code. To the VLIW processor specified above. Table 2 represents the occupancy of each functional unit during the execution of the assembly code in figure 1. So this is the table 2. And we have to fill in the instructions here. And for the assembly code given in figure 1, fill in the table 2 with the appropriate VLIW instructions. In your solution, minimize the number of VLIW instructions. This is very important. and ensure that each instruction is scheduled to execute as soon as possible. Table 2 should only contain assembly operations supported by the VLIW processor as described in table 1. Okay, so let's start. So we have this assembly code. So this is the first cycle. So in the first cycle, we can load the element A. So that is, we can execute this instruction V1 in the first iteration. So let's write V1. Now the next instruction is load. Should we execute it in the second cycle, or can we do it in the first cycle itself? So in the question, we were given that there are 2 load units. So we can do 2 loads at the same time. And also there is no dependency in A and B, so we can fetch both the elements in parallel. So we can also execute instruction V2 in the first cycle. Now let's see, can we execute more instructions in the same cycle? So can we execute the add? No, because we cannot add until both of these values are loaded. And can we also execute another load? No, because we only have 2 load units. If we had 3, then we could have also loaded the value of D in parallel in the first cycle. So we cannot do the subsequent instructions because these are dependent on loading the prior instructions. So in the first cycle, we can only do V1 and V2, and next all others would be like no instruction. Now in the second cycle, we can add both the things. So V3 and can we also load the value of D? So D is independent of A and B, so we can load in the same cycle as well, because the load units would now be empty because each instruction take 1 cycle. So we can also do V4 in the same iteration. And the next would be. So in the third, now we have done all these 4. Now we have multiply. So we have now value of R4 and R5, both from cycle 2. So in the next cycle, we can do V5, which is multiplication. Can we also do store? No, because we can only store after we get the multiplication result, which would be after this cycle. So we cannot do anything else in this cycle. And next cycle, we can store because we have now gotten the result in register R6. So we can execute this instruction V6 here. We cannot branch until we have stored the result. So we will execute the branch instruction in next cycle, which is here. So we have basically written, pipelined all of them, scheduled them. So this is the answer of part 1. And we have also minimized the number of VLIW instructions. So the maximum cycle that it could have taken if we just execute 1 instruction in 1 cycle instead of parallelizing them, then it would have taken us like 7 cycles, but we did it in 5. Okay. So what does the next part say? It says, what is the ratio between the number of useful operations and the number of VLIW instructions in your code? Show your work. So we are also given a hint here. A useful operation refers to any assembly operation that is not a no operation. So the number of useful operations here are 7, as we said: load, add, multiply, add, load, multiply, store, and branch. So there are 7 useful operations. And the total number of VLI instructions that we took are 5. So the ratio would be 7/5. Is it clear? Explain it again. Okay. So first of all, we are asked the ratio between useful operations and the number of VLIW instructions. So the hint is that a useful operation refers to any assembly operation that is not an OOP. So we have 7 such assembly operations. So here we have 7, and the number of VLI instructions are 5. 1, 2, 3, 4, 5, because we executed in 5 cycles. So the ratio becomes 7 by 5. Yeah. Okay. So the next part, what is the execution time in cycles of the VLIW processor when executing the sequence of instructions in table 2? Let me open table 2 again. Yeah. As a function of the loop counter n, show your work. So we have to tell the execution time in cycles. So how many cycles does this processor takes to execute like one iteration? So it's 5, as we saw here. And now this same thing happens n times because the loop counter is n. So we just simply multiply by n. So the answer becomes 5n cycles. I hope it's clear till here. So now we are at the last part where we have to calculate the energy consumption. So what is the energy consumption in joules of the VLIW processor when executing the sequence of instructions in table 2 again as a function of loop counter n? Show your work. And we are given that energy is equals to power into time. Notice we have power average here. So some students like make mistakes in this part. So first of all, let us calculate the power, and then we can calculate the time, which gives us energy. So power average would be, if we go to the first sheet, we are given here that the power consumption of a functional unit when executing a useful operation is 5. And we have 7 useful operations. So 7 into 5. This is for the useful operations plus. Now, how many no operations do we have? 2, 3, 4, 5, 6, 7. So we have 23 no operations, and the power consumed while executing no operation is 1 watt. So 1 divided by the total number of functional unit for 5 useful instructions across 6 functional units would be 5 into 6, 30. So it would be 35 plus 23 by 30, which is, so 29 by 15 is power average. So we got the power, now we have to calculate the time. So time, as we calculated here, the cycles in cycles. So it was 5n. To convert it into seconds, we need to like divide it by frequency. And here we are given that the VLIW processor operates at 1 gigahertz. So we can just do 1 by 1 into 10 raised to power 9. So we get 5n nanoseconds. So the energy becomes power average into time. So this would be in joules. Is everything clear? Okay. So yeah, that was all. Now Spiros will present the next questions. Oh, sorry.
All right, so our next question is going to be about prefetching. Specifically, we're going to study the behavior of a couple of different prefetchers on this particular access pattern of an application. And we're going to assess them in terms of coverage, accuracy, and bandwidth. We're assuming, of course, a processor with a single core, one level of cache, and a DRAM-based main memory system. So before we start, two things. First of all, we will only consider the steady state of the application. So that basically means that we don't care about particular edge cases. Like, for example, the first access will never be prefetched no matter what, because the prefetcher doesn't have a pattern to base its prefetches on. But in the steady state, it could be prefetched sometimes. So we only care about the steady state. And second, if there is a request to a cache block that has gone to the main memory, a new request for the same cache block will not go to the main memory as the outstanding request is not yet completed. Instead, the new request will be merged with the already outstanding request in the MSHR. So the MSHRs, I don't know if you've covered it in class, are essentially structures that hold outstanding cache misses, right? So what this essentially says, for the sake of this question, is that we essentially only care about which cache blocks are being fetched, not how many times they're being fetched. So even if the prefetcher asks for a prefetch twice, we're only going to count it once. First of all, let's take a look at the pattern itself, right? To see what sort of accesses are happening. So we go from A to A+1, so that means that there's initially a stride of 1. Then from A+1 to A+2, so that's again a stride of 1. Then from A+2 to A+7, which is a stride of 5. And then again, from 7 to 8, stride of 1, 8 to 9, stride of 1, 9 to 14, stride of 5, etc. So that means that we're essentially accessing three consecutive cache blocks, and then we have a sort of stride of 5, and then we repeat the same pattern. So let's see. For the first part, we first design a simple stride prefetcher that observes the last three cache addresses. If there is a constant stride S between the last three addresses, the prefetcher issues a prefetch to the next cache block using the stride S. Otherwise, it does nothing. So essentially, that means that if the prefetcher sees accesses to blocks A plus K, A plus 2K, then we will prefetch A plus 3K, right? Right, great. And our goal here is to measure the coverage of this particular stride prefetcher, where the coverage is defined as the quotient of the correctly predicted prefetch requests to memory requests. So that essentially means it's essentially how many of the actual accesses of the program the prefetcher actually managed to prefetch. So let's sort of see what accesses the program does and what the prefetcher prefetches each time, right? So on the one hand, I'm going to draw the accesses happening, and on the other, what the prefetcher is prefetching, right? Okay, so we start here with we first access A, right? The prefetcher hasn't seen a pattern yet, right? There is no sequence of strides happening, so it's not prefetching anything yet. Then we access A plus 1. That's a stride of 1. So the prefetcher, but there's no pattern yet. So the prefetcher is still not prefetching anything. Then we access A plus 2, which is again a stride of 1. The prefetcher now sees that there is a constant stride of 1 in the last three accesses. So it will prefetch A plus 3, right? However, unfortunately, A plus 3 is unnecessary because after that, the program will skip to A plus 7, right? So this is a stride of 5. The prefetcher now sees that the last two strides are different, so it will prefetch again nothing. Then A plus 8, again, the last two strides are different, so it will prefetch nothing. And then at A plus 9, it will now see again that there are two consecutive accesses with stride 1, so it will prefetch A plus 10. However, both of these are actually unused by the program, right? So that essentially means that since this pattern continues indefinitely, it essentially means that the prefetcher never prefetches something useful, right? So essentially, these are useless, which means that the correct prefetches are essentially 0, which also means that the coverage is 0. Okay, so that's part A. Any questions so far? Yes? What? Yeah, this particular this prefetcher would work well in some workloads, but in this particular workload, it just so happens that nothing which we prefetch ends up being used, right? This is specific to this particular pair of prefetcher and access pattern, right? Yeah, I hope that answered the question. Anything else? Yes. The pattern which you noticed and what you prefetch based on the pattern you saw depends on the design of the specific prefetcher, right? So this particular prefetcher, just its policy is if I see the same stride twice, then I will assume it will come a third time, right? So you see, this is essentially the edge case in which this particular prefetcher performs very poorly, because the workload is designed to have exactly the same stride twice, and then it goes to a different stride, right? Does that make sense? What? It acts on two things. I think it's mentioned here in the question, right? It observes the last 3 cache block addresses, and if there is a constant stride S, then it issues a prefetch, right? Yeah. Okay. So is it clear now? Excellent, great. So now the next question is, what is the accuracy of the stride prefetcher in this application, where the accuracy is essentially kind of the complementary to the coverage. It's essentially how many of the prefetches that happened were actually used, which is again the ratio of correctly predicted prefetch requests, but this time to the total prefetch requests happening. And we basically have this for free from above, right? Because since correct prefetch is equal to 0, we also have that the accuracy is 0. Does it make sense? Yes. Okay, great. So now for the next question, we now want to design a different kind of prefetcher, right? So we saw that the stride prefetcher didn't work, and we want to design a different one. So what does this prefetcher do? On a cache block access, it prefetches the next n cache blocks, and we see that this prefetcher has a coverage of 66.67% and an accuracy of 50%. And you want to see what is the value of n, right? Okay. So let's see what's happening in this case, right? So we have the program first accesses A, right? Then the prefetcher will go ahead and prefetch the next n blocks, right? Then it will access A plus 1. And the prefetcher will fetch n blocks after that, right? Then the program will access A plus 2, and the prefetcher will prefetch again and the n following blocks, right? So now we have its coverage and its accuracy, and we want to find what exactly this n is. So let's see. In terms of coverage, right? just so it makes sense again, coverage is how many of the accesses that are happening the prefetcher actually gets, right? So these two, and correspondingly, for example, A plus 8 and A plus 9 or whatever, after the pattern has, like in the second iteration, we will get them anyway. So in every block of 3 consecutive accesses, the last 2 we will get anyway, right? So the only question, so the only 2 things can happen depending on the value of n. We either prefetch 2 of the 3 in every 3 consecutive, or we prefetch all 3, right? So there are essentially 2 options. So we can either have a coverage of 66.67%, or we can have a coverage of 100%, right? So, and that depends entirely on the value of n. The thing is, if n is too large, it will eventually prefetch A plus 7 as well, right? So if that happens, then our coverage essentially becomes 100. So we don't want that. So that means that we need to have n relatively small, right? So since since we now know that n has a relatively small value, we should just play around with different values of n until we find this accuracy of 50%, right? And note that another observation here is that as n increases, you will prefetch more of the things that are in here in the A plus 3 to A plus 6 range, right? Which we don't need. So that essentially means that what we expect is that if we increase n, the accuracy drops, right? Does that make sense? Yeah, I mean, if you increase it, but without it reaching up to the A plus 7, right? So you're essentially prefetching more of these which you don't need, but you're still getting these anyway, right? So let's see what happens if we try n equals 1, right? What happens in this case? We have accesses again from the program, and then we have prefetches. So the program will access A, and the prefetcher will prefetch A plus 1, right? Then the program will access A plus 1, and the prefetcher will access A plus 2. Then the program will access A plus 2, the prefetcher will access A plus 3, right? And then this pattern essentially will repeat when we go up to down to A plus 7, right? So let's see. Out of these, so the prefetcher prefetched 3 blocks, and 2 of them were necessary, right? So that means that the accuracy is 2/3, which is more than 50%, right? So that means that n is still too small, right? So let's try n equals 2 now. For n equals 2, let's see again, accesses and prefetches. All right, we access A, and this time we prefetch A plus 1 and A plus 2. Then we access A plus 1, and we prefetch A plus 2 and A plus 3. And then A plus 2, and we prefetch A plus 3 and A plus 4, right? So we essentially prefetched 4 distinct cache blocks, right? But out of them, only A plus 1 and A plus 2 were useful. So that means, so 4 blocks prefetched, and 2 were useful. So that means that accuracy is 2 out of 4, which is 50%. So that means that n is actually 2. Does that make sense? Yes, see, it will continue because there is no overlap, right? So when we fetch A, we will then, sorry, A plus 7 is the one that comes after that, right? So after A plus 7, we will prefetch A plus 8, A plus 9, right? Then we will get, we will ask for A plus 8 and prefetch 8 plus 9 and 8 plus 10, and so on and so forth. It will be the same because there is no overlap. So this pattern will continue. Yeah. All right, so moving on, now we'll concern ourselves with bandwidth, right? So bandwidth is defined as request to main memory with a prefetcher versus request to main memory without the prefetcher. So now we want to find the bandwidth overhead of the prefetcher in the previous question, right? For n equals 2, right? So let's see. What accesses do we make without the prefetcher? Without a prefetcher, we prefetch accesses we perform accesses a plus 1, and a plus 2, right? So we essentially make the accesses between a and a plus 2, which is 3 accesses. With prefetcher, we will still access a up to a plus 2, but as we saw above, we will also access a plus 3 and a plus 4, right? So in this case, with the prefetcher, we are accessing everything between a and a plus 4 inclusive, right? Which is 5 accesses. So the bandwidth is 5/3 the bandwidth overhead. Does that make sense? All right, then. Moving forward, what is the minimum value of n required to achieve 100% prefetch coverage of the given application? So now we're getting into what we were talking about before, right? Remember that if we if n becomes large enough, it will eventually wrap around and also prefetch a plus 7, right? Which is what we want in this case in order to achieve 100% coverage. So what is the smallest n for which we can achieve that? Any thoughts? Yes. Yes, exactly. It's 5. Because essentially what we want, basically in the smallest case, the prefetch that originates from the access to a plus 2 is the one that will get a plus 7, right? So we want the access to a plus 2. We want the prefetch request from a plus 2 to include a plus 7. So that means that we want n equals 5. Or whatever, n greater or equal to 5, whatever. So 5 is the answer. Great. And now finally, what is the bandwidth overhead at this value of n? Yes? Okay. Yes, what? Okay, yeah. Remember that when the value of n was small, which was what we were assuming in the previous question, right? We were prefetching, we were getting a plus 1, a plus 2, getting up to a plus something, right? Basically, you will get from a up to a plus something, a plus 1 up to a plus something plus 1, and a plus 2 up to a plus something plus 2, right? If n is very small, then you won't be able to catch the next, catch a plus 7, which is in the next sort of block of consecutive cache blocks that we were accessing, right? So the thing is, you need to have, you need to make n large enough so that at least one of these 3 sets of prefetches will cover a plus 7, right? Yeah, I mean, technically, for larger values of n, this can have, you will prefetch a plus 7 earlier, right? You will prefetch it, like if n equals 7, you will even prefetch it from a, right? But essentially, we want the shortest case, the smallest possible n, which means we want the n for which the access at a plus 2 is the one that that will give us a plus 7. So you need to prefetch 5 blocks ahead, because 7 is 5 blocks ahead of 2, right? Does it make sense now? What? Yeah, exactly. You're gonna prefetch the next 5 blocks. Yeah. It increases what? Yeah. Exactly. Yeah. I mean, yes. Exactly. So you don't want, in a real system, this could lead to something like having a too massive of an n would lead to a lot of bandwidth overhead because you would be prefetching a lot of things that would be useless. This scenario is a little artificial, so like accuracy wouldn't drop if you increase n further, but in a real system, that would happen in general. You would generate a lot of unnecessary requests to the main memory. And now finally, what is the bandwidth overhead at this value of n? So again, let's see what accesses are happening this time, right? Accesses and what we're prefetching, right? So we are accessing A and we're prefetching A+1 through A+5. We are accessing A+1 and then we are prefetching A+2 to A+6. And we are accessing A+2 and then prefetching A+3 to A+7, right? And then when we continue ahead, we access A+7 and then we will prefetch A+8 to A+12, right? And so on and so forth. So now, remember that bandwidth, as we saw before, is defined as request to the main memory with the prefetcher versus request to the main memory without the prefetcher. So, so again, the accesses without the prefetcher, they are 3 as before, right? A+1, A+2. But with the prefetcher, how many accesses do we have now? Note that we're essentially accessing everything between A and A+7, right? And then again, we'll access A+7, and we'll access everything with A+7 through A+14, right? So the answer in this case is essentially, actually, if you look just at this, it would be a little tempting to say that with the prefetcher, we have 8 accesses, right? Because we are accessing everything between A and A+7 inclusive, right? But in this way, we would be essentially double counting A+7, right? Because we're going to count it in the next sort of block of consecutive accesses that we do. So this essentially means that with the prefetcher, we are accessing 7 blocks, if that makes sense. And of course, that means that the bandwidth will be 7/3. Essentially, yeah, basically, yes. For essentially, like, if you look at it in sort of a steady state, note that if you take like A to A plus like 70 or whatever, or some large number, you'll note that we will get essentially access everything with the prefetcher, but without the prefetcher, we will essentially only access 3 out of 7, right? So essentially, that's why the bandwidth is 7/3 in this case. Yeah. Exactly. It's essentially the ratio of how many addresses you're accessing with the prefetcher versus how many would be the program itself would access if there were no prefetching, right? All right. So yeah, this last question was a little tricky, but yeah, that's it for prefetching. Now, our final question is we're gonna end things a little bit lighter with some ISA versus microarchitecture questions. So this is a bit of an easy question. Yeah, we subtract 2 points for each incorrect answer, but hopefully you won't have any points subtracted. You guys should get all of these correct. So essentially the one thing to keep in mind with these ISA versus microarchitecture questions is that essentially the question you should ask yourselves is, should the programmer or the compiler or maybe the OS take this into account when trying to write correct software? If so, it belongs to the ISA. If not, it's like in the sense that if the programmer doesn't need to know about this in order to write a correct program, then it's part of the microarchitecture, right? Yes? Yeah. For example, in some cases, yeah, you might make optimizations based on the like for example, you might make optimizations based on the underlying architecture, right? But you shouldn't have to know about that in order just to get the program to do what you want it to do, right? So with that in mind, I also want to follow back on a question you asked a little bit earlier, right? About virtual memory specifically, right? So just to be clear, asking whether virtual memory is ISA or microarchitecture is a little too general. There's no reason anyone would ask that, right? But in general, virtual memory has to do with the sort of hardware-software contract, right? So the software has to be aware of most aspects of virtual memory, right? Like for example, the page table walker, like the page table structure, right? That it is it has this sort of radix tree form, right? This is filled by the operating system, so it can't be transparent to the software. Or for example, sometimes you want to invalidate a TLB, an address in the TLB, right? Because when you free memory, you have to sort of destroy the underlying mapping, right? That this virtual address maps to this physical address. If that's stored in the TLB, someone has to tell the TLB that this mapping is no longer valid, and that is done by the OS with specific assembly instructions. So in that regard, these aspects of virtual memory are ISA related. Some microarchitectural aspects of virtual memory would be, for example, L1 or L2 TLB size or associativity. Like you don't have to know these in order to make a correct virtual memory system or whatever. Yes? Yes. In what sense we can't do anything?
Well, it's not like we can have an instruction that changes this.
That changes, what? We can't have an instruction that changes?
So, instruction set architecture, there's no instruction that we as a programmer can use to affect that behavior, right?
No. For example, you can change the page table structure. The page table structure is part of the contract between the programmer and the hardware. So it is specified in the instruction set architecture, for example. You cannot change that. Why? Which things you can't? yeah, that was a little bit too much, maybe. But yeah, in general, don't worry about it. Like most aspects of virtual memory are related to the ISA.
Yes.
All right. So now, with that out of the way, branch misprediction penalty. Would you say this is more of a microarchitecture or an ISA? Yes. Exactly. Yes. You don't have to know what the branch predictor does in order to write a program, right? So number of privilege levels. This is exactly, yes. Privilege levels essentially. First of all, this is ISA. The instruction set architecture will often define certain privilege levels, which means which essentially dictate which instructions can be executed by whom, right? And like there are some instructions that you need elevated privileges in order to execute. So this essentially helps helps sort of organize operating systems a little better, right? Because if there are some critical, for example, memory accesses you have to perform, you have to make sure that a regular user cannot perform them and only the OS can do them, right? So the way you do this is with the privilege levels. You essentially set a privilege level when you set a privilege level to a specific degree, you may not be able to, you cannot execute simple instructions or whatever that require to addresses that may require elevated privileges or something like that. Yeah, exactly. And the number of cache sets at each level of the cache hierarchy, that's exactly. Instruction encoding for control flow and branch instructions, that would be. Exactly, yeah. Like the idea is, this is essentially, for example, what is the opcode for control flow and for a branch instruction, right? So like the compiler cares about that because it like this particular encoding changes the binary that will end up being you compile program into, right? So you need to know what each instruction, what the encoding of each instruction is, right? Yes. Exactly. Yeah. The ISA defines that. Yeah. And yes, the ISA defines that so that on the one hand, it's the compiler's responsibility to make sure that, for example, a load instruction has this particular opcode or whatever. And on the other hand, the hardware will have some fixed hardware that will see, when I see this opcode, I know that it's a load instruction, right? So this is a part of the contract. So it needs to be part of the ISA. Now, number of instructions committed at each processor cycle in a superscalar processor. Yes? Exactly. Exactly, yeah. The programmer doesn't need to know about that, really. And number of arithmetic logic units, that is, yes? Also, for the same reason. Now, whether or not memory accesses are aligned at word boundaries. So this essentially means that, there are some instructions in the ISA that say load word, which will load like 2 or 4 bytes at a time. And the question is whether these bytes should be, like, for example, whether an access to a 4-byte, like whether when you read a 4-byte word, it has to start at a multiple of 4, or it can start in between. Yes. Actually, no. This is interesting. This is defined at the ISA level, whether this is allowed or not. Yeah. Here's the thing. I think, maybe there are some instruction sets that sort of allow this, but here's the thing. It's a little difficult to implement in practice in actual hardware, right? Because the hardware reads stuff at cache block granularity, right? So essentially, if an axis is misaligned, there's a chance that the hardware will have to fetch two cache blocks at once. I know this is a bit of this is a sort of limitation of the hardware technically, but it would be sort of so difficult to implement in hardware that some ISAs just disallow it altogether. Yes. Yeah. Exactly. It's exactly like that. Yeah. Exactly. Yes. So that is part of the ISA. Yes. And the memory addresses of exception handlers. What would you think this is? Yes. Exactly. Yes. Because here's the thing, right? When an exception happens, the hardware will start, will essentially jump, will change the program counter into a particular position, which is where the exception handler lies, right? That's all the hardware has to do. But then what actually runs after this jump, like what instructions lie in there, like someone has to place these instructions there, right? There will be like a function or whatever that's the exception handler. Someone has to place that there. But how are you going to place that there if you don't know where the address is? So you have to make that part of the ISA. Yes? I'm not sure. Yes, exactly. Yes. Exactly. Yeah. Exactly. So yeah, after that, where address generation bits are located for load and store instructions. We've already, yeah? Exactly. It's essentially the same logic as, which one was it? Number 4. Exactly, yeah. It's the same as logic as number 4. And finally, number of entries in the instruction window. Yes? Exactly, that's essentially how big the row buffer is. The reorder buffer, sorry. Yeah. And I guess that concludes this problem-solving session. Hey, thank you for bearing with us for so long. Hey.